We now consider the D and L system of nomenclature as promised. So what do these D's and L's mean anyway? Well, if you look at the Fisher projection of all the D sugars, and I apologize for this slide being so crowded, but we've got to have this information on it. What you should notice, the one pattern of all of these Fisher projections, is that the OH on the bottom carbon, which is the furthest from the carbonyl group or the highest carbon number, is always on the right side. Okay, so look at all the ones in the top row, the 6 carbon sugars, the 5 carbon sugars, the 4 carbon sugars, and the 3 carbon sugar. In all cases, that OH is on the right side, and that is what defines a D sugar. If the OH carbon is on the left, then it is an L sugar. So does this have anything to do with dextrorotatory and levorotatory, which are words that start with D and L and may come to mind if you think about the letters D and L? Well, dextrorotatory, of course, is the other word for something having a positive optical rotation, and levorotatory is the word for something having a negative optical rotation. So if you analyze the D sugars on the previous slide, 9 of them have positive rotations and 6 of them have negative rotations. Okay, so negatives are glucose, ribose, arabinose, lysose, erythrose, and threose. The rest are positive. So the D sugars are not all dextrorotatory. The D sugar that is dextrorotatory is D-glyceraldehyde on the bottom here, which is the parent of this family. So what we have done in this slide is given you the whole family of D sugars, which have been arrived at from adding additional carbons between the glyceraldehyde stereocenter and the aldehyde at the top of the Fisher projection. Okay, so if we add 1 carbon to glyceraldehyde, we can either put the OH on the right, which gives us D-erythrose on the left side of your diagram, or we can put the OH on the left, which gives us D-threose. Because there are now 2 stereocenters, these molecules are diastereomers of each other and therefore are worthy of different common names. Okay, so now if we add a 5th carbon above the 4th carbon, that introduces another stereocenter. So now there are 4 diastereomers, and that's how with 5 carbons we have ribose, arabinose, xylose, and lysose. And then finally, adding a 6th carbon gives us the 8 D-aldol hexoses that we have already met in a previous lesson. Obviously, each of these structures has an enantiomer, the corresponding L sugar, so there are twice as many total stereoisomers. For the purpose of this lesson, I'm just focusing on the D sugars because those are the ones that occur naturally. So what is the same about all of these structures is the absolute configuration at the carbon furthest from the aldehyde. Okay, so in all of them, as I've said, the OH is on the right side, and that is what makes them D sugars. So when you look at a Fisher projection of a sugar, and you need to know if it's D or L, you just have to look at that stereocenter furthest from the aldehyde. If the OH is on the right side, it's D. If it's on the left side, it is L.